Welcome back, guys. So in the earlier video, we had discussed about how a charged particle Q moves in the magnetic field. So in this video, I'm going to tell you how the charge moves in the presence of both electric as well as the magnetic field. Okay. So let us draw our coordinate axis as usual. So in this case, I'll consider my magnetic field. Okay, I have to define it first. So let me define it as z-axis, x-axis, y-axis. Okay. In which case, I'm going to take my electric field along the y-axis, and my magnetic field is along the z-axis. Okay. So I have a charged particle Q here, and I'll consider its velocity in the direction of the x-axis. So I need to now figure out both the electrical force as well as the magnetic force and its direction. So figuring out the magnetic force is very easy, which is given by the screw rule. Let us see. Okay, we have the v vector here and b vector here, and we have the v cross b vector in this direction. So that would be like this, that is the clockwise direction, that is in the xz plane. Okay, so I have to consider it like this, in the clockwise direction, and the force would be downwards. Okay, so the magnetic force is in the downward direction. That's the magnetic Lorentz force. Now for the electric force, it is always in the direction of the applied electric field. Okay, a charge experiences an electric force in the direction of the applied electric field because we have considered this charge to be positive. Okay, so I'm going to say my electric force is in this direction. So since we have now defined both the electric force and the magnetic force, let's get to its mathematics. Okay, now the total force, capital F, experienced by this charge in the presence of both electric as well as the magnetic field can be given as as we have discussed earlier in many classes, charge times the field. So what is the field here? We have both the electric field plus we have the magnetic field, that is v cross b. Fine. Let's remove the brackets. We get QE plus Q times v cross b, right? So this is what? This is nothing but the electric force, I'm sorry, and this is what? This is nothing but the magnetic force or magnetic Lorentz force. Okay, so our total force is comprised of the force due to electric field plus force due to the magnetic field. Now if we figure out a way, okay, to balance both the electric field as well as the magnetic field, because in this diagram, as you can clearly see, the electric force is in the y-axis direction, positive y-axis direction, and the magnetic field is in the negative y-axis direction. Since these two are vectors and they are in the opposite direction, so if the vectors, if the magnitude of these two vectors were to be equal, then they would cancel out each other. Okay, so in which case our particle would experience no force at all, because if there is no electric force and there is no magnetic force, there is no other force. Okay, so our particle will move in this x-axis direction only, but if not, then these both two forces will act on the particle and it will make it to deflect from its original path. Okay, so what we have to do to make the particle undeflected in these two fields is we have to make the magnitudes of these two forces equal. So now what is the magnitude of the electric force? There is nothing but Q times E. And what is the magnitude of the magnetic force? QVB, QVB sine theta. So in this case, theta we have taken to be 90 degrees. So sine 90 would be 1, which is the maximum. So our magnitude becomes just QVB. Okay, so if FE equals FB, then these two forces will cancel out each other because they are in the opposite direction, and if the magnitude becomes equal, they cancel out each other, and our particle Q, charged particle, moves in its original path trajectory or original trajectory in which it was put into. Okay, so now equating these two, what do we get? Equating the magnitudes of the electric as well as the magnetic force, we get QE equals QVB. Q cancel outs, and we have the equation for velocity as E by B. What is the physical significance of this equation? If you look at it carefully, it means that if a charged particle Q is having this particular velocity that is decided by the electric field and the magnetic field, if it has this particular velocity, it can be any number, but that is decided by the electric field and magnetic field. If it has that particular velocity, then it moves undeflected in the presence of both the electric as well as magnetic field. So what is the use of it, if you ask? So the use of it is it is something sort of like separating things. Okay, so let's say we need the particles. Okay, let's say we have both electric field and magnetic field, or let's say we don't have them. Okay, in a scenario, let us construct a scenario in which this equation would be used. Okay, let's say we want to charge particles of this particular velocity, say v. Okay, we want all the charged particles. I have a bunch of charged particles and I want all the charged particles with this particular velocity v. Okay, now how do I get it? Okay, so what I do is I set up my electric field in this fashion, magnetic field in this fashion, and what I do is I select my magnitude or the value of my electric field and the value of my magnetic field in such a way that the ratio gives me the velocity which I need, velocity of the charged particles which I need. Okay, for instance, if it's going to be, let's say I need 10 meter per second velocity charged particles, then I'm going to choose my electric field as say 20, and I'm going to choose my magnetic field magnitude as 2. Okay, say 2. Okay, so what does this ratio yield? It yields 10. So what I've done is I've chosen the velocity, my required velocity, by setting the electric field as well as magnetic field. So when I do this, all the particles having this particular velocity I will only get these particles, and the other particles having different velocities will get deflected by both the electric field and the magnetic field. So I get all the particles which are having only this particular velocity. So by keeping in mind which, we name this equation as the velocity selector. This is all about the motion in electric and magnetic field. If you have any questions or doubts, hit me up in the comment section, and in the next session we'll discuss about the cyclotron.